Hello everyone, let's take a look at our next problem. The equation 9 to the x minus 3 to the x plus 1 equals k has one or more real solutions precisely when k is greater than or equal to negative 9 over 4, k is greater than 0, k is less than or equal to negative 1, or k is greater than or equal to 5 over 8. Interesting. So my first instinct here is to replace the 9 with a 3 squared. And then, we have things in terms of just a base 3. Has one or more real solutions. And then maybe it's worth looking at the graph of the function. Think of the thing on the left as being a function of x. Look at the graph of it and calculate its minimum and or maximum values. What else could we do? Maybe try factoring out a 3 to the x or something. I'm not exactly sure what might be a good approach here. Well, I can see right now that if k is equal to 0, we're looking for 3 to the 2x is equal to the 3 to the x plus 1. This implies x is equal to 1, right? Then on the left-hand side, we have 3 to the 2. On the right-hand side, we have 3 to the 2. Oh, but k equals 0 is not one of the options. Option B is k is greater than 0. And option A, which is k greater than negative 9 over 4, does sort of, this is one particular case of that. So let's get rid of this and think of another way of approaching what we have here. I suppose we can eliminate option B, which is k greater than 0, because we've shown that if k is equal to 0, then there is a solution. And the way the question is worded, it says that this equation has one or more real solutions precisely when. Now, given the logic that I've just worked out there, the fact that there is at least there is exactly one solution when k equals 0 means that the answer to this question has to be A, k greater than or equal to negative 9 over 4, because that's the only of these options that includes allowing k equals 0. But it would be nice to sort of derive that solution more directly rather than just eliminating all 3 of the other solutions. So let me see if I can think of a way of doing that. Maybe it'll be by finding the minimum and maximum value of k, the minimum and maximum value of this function of x on the left-hand side. So there is no maximum, because as I allow x to approach infinity, this term will grow faster than that term. So it's unbounded from above. What if I take a derivative and set it equal to 0 and try and find a minimum? Okay, so I found a critical point of this function. I had to refresh my memory on exactly how to take the derivative of exponential functions in a base other than e. Whatever, did some algebra here, and I found a value of x which gives a critical point. I believe this has got to be a minimum, right? What does this function look like as I take x to negative infinity? As I take x to negative infinity, this thing will be equal to 0. Equal to 0. Then it has some critical point, a horizontal tangent, which would correspond to either a minimum or a maximum. But then it goes off to positive infinity. So this horizontal tangent has got to be a local minimum, which would make it a global minimum. So let's substitute now this value of x into the function and see what we get. Can I simplify this value of x first of all? Okay, maybe a little bit simpler depending on your perspective. Yeah, but I want to compute what the value of the function is at this value of x. Oh, I'm not going to set this equal to k. I just want to figure out what this is equal to. This is f of x star. Yeah, so I kind of saw this coming early on, like around here. But I just wanted to go through all of the logarithms and exponents and arithmetic and so on to actually make sure, and so you could see that the computation actually works out here. So what I've shown here, let me summarize some of the steps. I took a derivative of our function and set it equal to 0, and then solved for x, and this gave me a critical value of x, meaning there's going to be a horizontal tangent to the function there. And then just sort of in my head, I figured out that as I take limits as x approaches negative and positive infinity, you know, when x goes to negative infinity, this function levels off at 0. And when it goes to positive infinity, it blows up to infinity. And so the only option for a horizontal tangent is at a minimum, a local minimum, which would then, of course, be a global minimum. And then by substituting that value of x star into the function, the global minimum of this function is negative 9/4, which is exactly the answer that I said we should have originally. Negative 9/4 is the first of the 4 options. Yeah, so I solved this in 2 ways. The first way was kind of cheating, simply by recognizing that when k is equal to 0, I can solve this. And so none of the other 3 options allow for k equals 0, and so they can't possibly be the correct answer. So that was by process of elimination. But my second approach here was a little bit more precise, and you know, it would work if we were given different multiple choice options here that also included k equals 0, then my previous technique wouldn't have worked. Only this sort of direct approach to compute the global minimum of the function would have worked. Yeah, I'm pretty confident in this answer, but if I have any more comments or if I find some kind of mistake, then I'll put them in the description below. Otherwise, thanks for watching.